is Järveläinen. I come from Premix, and we are a Finnish company manufacturing plastic. So you can guess that the following presentation will be a bit different from the previous ones. So you will not hear anything about the latest release. I don't know if it's a good or a bad thing, but that's the case anyway. So this is more a general presentation about materials and maybe how you should think about them and take them into consideration in the future 5G designs and maybe other wireless applications as well. So it's a short menu, but I will have some general requirements and then some concrete examples. And I will also focus on cost just a little bit, because I know that everyone here should care about what things should cost or cannot cost. And then in the end I have the link to AWR, the reason we are here. So you have all seen this kind of vision picture about what will happen in the next decade, and everything will be connected and so on and so on. And we have new applications, new frequencies, and so on. What I want to focus on a bit, beside the kind of obvious things, is that we will have like drones, flying objects. What to care about in drones is, for instance, weight. How much some antenna weighs will have a big difference, because that will relate to the battery time, the flying time of the drone. Then also weather conditions will affect things. If you have something outdoors, it has to withstand temperature, humidity, ice, snow, impact. So there are quite many different aspects you should take into consideration when choosing materials. If we look at the 5G spectrum, compared to previous generations, you will notice that there are much more frequency bands. Okay, nothing strange with that. But then there are also more local. Japan will have some bands which China does not have, and Europe has some third bands, which means that you will have much more designs, because you cannot copy easily existing designs because you will have so much frequency bands. So in 4G, it was maybe you were able to take one design and use it everywhere, because there were more kind of common standards. And then you have also heard about the auctions. Of course, it's about money, and the sums might seem ridiculous if you don't know what you do with the spectrum. But you might be in a situation that some hardware manufacturer, Kathrein or Comscope, they partner with several different operators at different bands. So they will make this band for this operator and this band for the next operator, and so on. So it means that the same OEM will really have many different very frequency and operator specific designs. So you will have much more. This is a good thing for us, probably, because there is more work to do, and you have to adapt almost the same solution to different frequency bands and different applications. Then, to have some kind of overview what different sectors want in 5G, there will obviously be some fights, because we don't want the same thing. Nokia or Ericsson want to sell hardware as much as possible. The operators want to buy as few as possible, and they want to cover as much area as they possibly can with the base stations. And then we as users, we just want the kind of 5G to work everywhere, no matter if we're in a subway tunnel or somewhere in the woods. We just assume that it works everywhere because this is the latest technology. Of course, that's not the case either. And then maybe an aspect which is not obvious is the environment. How much waste do we do? How much energy do we use to transmit the signal? I read about some guidelines for 5G base stations, and one limit was that you can use something like 32 kilowatts for one base station. And that's, if you would make a sauna with that energy, it would fit 17 people. So it's a lot of heat. But you rarely kind of hear about what you plan to do with the energy waste. How do you plan to make some considerations for the environment as well? But we as a material supplier, of course, we want to believe that there is some kind of compromise so that everyone can be a winner at the same time. So of course, everyone does not get everything they want, but everybody gets something which can bring money to the company. And why we care about dielectric materials is, of course, because we have them everywhere. Sometimes they are wanted. Your antenna should work on some different frequency bands, and you can use a material to kind of change the size of an antenna or something like that. And sometimes you don't want it there, but you need it. You need some structural support, you need some radom, which from the signal point of view is just unnecessary. It just protects it from humidity or dust or whatever like that. So this is maybe a bit exaggerated, but the point is that you don't want to make heat out of your signal. You want it to go to the user. So when your phones and devices get warm, that's unwanted, obviously. And I'm not saying that it's due to the dielectric materials, it's maybe because of some other components inside, but still, the point is that you don't want it to happen, but it happens because of physics. And now talking about 5G, I want to focus especially on the higher frequencies and just give a very, very simple view on why we should care more about the materials when we move up in frequency. So if we just assume a short microstrip line, we compare two materials. One is a bit lossier than the other. Then at the old frequencies below 6 gigahertz, there is almost no difference. But when you use the same materials, assuming the same material properties, and going up to 70 gigahertz, you have a much bigger difference. So I would assume that 20% is something you should care about. So we should at least know what materials we're using and how they behave when we go up in frequency. Okay, I will just have some, let's say, more or less obvious requirements from the material point of view. When you're an RF engineer, of course you don't want any losses in your material because you don't want to convert your signal to heat. But it happens, but of course you should know it. If you design your antenna at millimeter waves, you want to know how they behave at those frequencies. And then if you can choose, you will always have them as low as possible. Then the dielectric constant, of course, maybe you assume that you read in the simulator that it has some specific value and it works like that every time at all frequencies. That's not the case always, so we would like them usually to be quite flat over frequency. And at least we should know how they behave at the band you are designing your system on. And actually, during the past month, I have received many questions that can you tune this somehow, that the material behaves actually differently at different frequencies, that you have some kind of frequency selective permittivity. I don't know if you have thought about that, but this question has come to me twice during the past month. So maybe this is not a good thing that it's so flat. Maybe we should have some kind of selectivity. Then, when you produce a material, you assume that it's the same material. When you order today and when you order next week and next year, it will be exactly the same. In real life, when we produce something with real machines, not in a simulator, but we have the real world, we have many factors which change. For instance, humidity. if you produce it in the winter and in the summer, you will have a bit different conditions. And everything affects the final product. So you really want it to be stable. The telecom standard is something from minus 40 degrees to plus 85. So you want it to work also in different temperatures. You want it to work in Sahara and in Russian winter. And you want the materials, your application should work in the same way in different humidity conditions. So the weather should not impact the performance of your device. And again, usually we cannot make it perfect, but we can at least minimize the damages. We can make it as good as possible. And at least if you're not able to control it, you should again at least know how your device behaves in different environments. And talking about cost, you want injection molding if you want to do mass production, because that's usually much cheaper. And all of the above mentioned properties, you want them, but you will not maybe get them always at the same time. But just to have some thoughts about what to consider and what we can require in our designs. I have a few examples of how we can change the material to make some difference, not in the performance, but in some aspect. In this case, this is a paper from Aalto University this year, and this is an E-band beam scanning lens, and they first made it from Rexolite, which is a very good RF material. It has low losses, and it's in a way everything you might want from a material. But the only downside is that it's quite large. And I don't know about all of you, but many times I hear that the RF engineer or system designer makes some design, and then there is somebody saying that no, it's too big. You have to make it flat. So the form factor is something somebody cares about in the end. So even if it works perfectly, it's not good looking or something like that. So then one way to just decrease the size is obviously to just choose a higher permittivity. So in this specific case, you could get a 25% volume decrease, and still the performance was actually identical. So you don't change anything else than the size of the antenna. The second example is from an automotive radar application, and we looked at the radar material. You can maybe guess where I'm going already, but depending on what kind of material you choose, you will have different results. So the PBT plus glass fiber is a very common material, and it has very good mechanical properties due to glass fibers, for instance, inside the material. And it gives it very good mechanics, but at the same time the fibers have some effect on the RF performance. And if you would choose a less lossy material, of course you will get better performance. Your radar will see a bit longer. And in this case we get this 0.7 dB difference. Is it a lot? I will come back to this. We also made a measurement with 24 gigahertz, again comparing different materials, and happened to get to the same number. In this case, also 0.7 dB difference. The number is not important, so don't. That's not the point. But what does it mean to have this kind of difference? Is it a lot or not? When you convert it to percentage, you will notice that actually if you would use the less lossy material, you could have 17% larger coverage, just because your material does not convert signal to heat as much. So in the end, it means that if you want to cover a city with base stations, you can you can do it with less number of antennas. So instead of choosing bad materials which cost a bit less, you should think about how much you pay in the long run, how much it will pay in a city-wise deployment of base stations, for instance, or how much longer your radar can see in some other application. And we also have one customer who makes very good antennas, but they happen to be 3 times as expensive as their Chinese competitors. And you would assume that with this difference in price, nobody can sell anything. 3 times is a way too much, but they are still doing business, and what they are kind of telling on their homepage is that you can really survive with much fewer sites to cover the same area with the same capacity. And at the same time, you can be more energy efficient, so you don't need as much energy to cover and give the coverage you need. So somebody is believing that you can buy a bit better materials and still make a business, and a good business. So when you look at cost, you cannot just say that, okay, material 1 has this many euros per kilogram, the second one has this many, and then let's choose the cheaper one, and we still get it fulfills the specs, but still you should think about the big picture, and also how it affects the whole life cycle of a product, and recycling aspects as well. So you still wonder that why do we talk about the plastics in this kind of seminar? And we had this kind of cooperation between AWR and also with Opteni. So we just did a small demonstration with Antsin. So kind of a simple dual band Wi-Fi MIMO antenna. And in order to verify the simulation, we also did a prototype, and actually it was me and Jaakko who did this very beautiful soldering here. And so it was not done in some very clean lab, but it was a very simple demonstration. And still, when we compared the prototypes with the simulation, we have a very good match. So here we did 2 prototypes, and I think was it Antti who measured something, maybe. So what you can say is that if you get these good matches, is due to the software. Software performs obviously good enough. Models with sufficient accuracy and good enough meshing. But then also the materials are known good enough that you can achieve these kind of results. And basically, we as a company care about what you can do with plastics, for instance, what you can do with materials, what you can do in the mass production or in prototyping, and then you need some simulation software in between to get the final design. And of course, we hope that in the next step is that you do some mass production and everybody gets €1 billion or something like that. Okay. So my conclusions are simple. When going up to frequency, we should know at least what materials we're using, and we should think about the consequence of using all materials when going 10 times higher in frequency, because it makes a difference. And then we cannot always just think about RF properties. We should also think about weight and different weather conditions and how they affect the performance. And when you calculate the cost, you have to calculate it more than just the material cost itself or some component or some technology. But how much will you pay for the whole deployment of your city or your mall or subway station or something like that. So, thank you. Do you have any questions?